Hello, my name is Allan Freitas and I'm from Federal University of Paraíba, Brazil. I'm going to talk about volume comparison and rigidity results on static metrics. And first of all, it's a pleasure for me participate of this virtual workshop on Ricci and Scalar curvature. I thank especially Professor Cristina Sormani by this kind of opportunity, especially for young mathematicians. Okay, let's introduce our problems. And first of all, we talk about comparison geometry, where the question is how does curvature influence the metric geometry of a Riemannian manifold? And by metric geometry, we mean lengths, areas, volumes, distances. We can approach about compare Ricci curvatures of underlying manifolds. For example, we have the definition that an Einstein manifold is a manifold where the Ricci tensor is a multiple constant of the metric. And a natural question is what's the relation between Einstein manifolds and its volume? Answering this question, we have the famous Bishop-Gromov's inequality that said that if you have a complete Riemannian manifold and compare its Ricci curvature with a curvature of a space form, then we can compare the volume of a ball, a geodesic ball, in this first manifold, and a ball in a space form. Okay. Furthermore, checking the proof of the Bishop-Gromov's inequality, we can see that we have a statement of rigidity. This is, if you have the equality, this happens if and only if the ball, the geodesic ball in the first manifold is isometric to a ball in a space form. Okay. On another hand, we approach with static manifolds. And for us, a complete Riemannian manifold with boundary is static if it has a static potential in the following sense. A static potential is a non-trivial solution to the static equation. That is this equation where this is Laplacian of the function, this is the Hessian, and this is the Ricci tensor of the manifold. Okay. We observe that if a Riemannian manifold has a static potential, we have many restrictions in the geometry. For example, if you take the divergence of this equation, you can prove that the manifold has constant scalar curvature. And if you consider these level sets of 0, we can prove that these IP surfaces are totally geodesics, and we can call these manifolds of apparent horizons. And these functions, the norm of gradient of the static potential restricted to this IP surface that are called surface gravity, are positive and constant along any connected component of these sets. The main motivation to study static manifolds relies in general relativity, because when I study solution of the Einstein equations that are static in a sense, we can solve the Einstein equation using static potential in the following sense. The statistic equation is equivalent to assertion that this Lorentz metric G bar, okay, where here we have the static potential, and here the initial static metric, and this new metric, Lorentzian metric, is a solution to the Einstein field equation in the vacuum. Okay, that is this equation here. And in the case in the vacuum, we have that this momentum tensor vanishes, so the right side of this equation vanishes. So it's equivalent in this case, find a static potential and solve the Einstein equation in the vacuum. Okay. And to fix the notation, a stat tribe is a complete Riemannian manifold, okay, connected also, where the static potential vanishes precisely on the boundary of this manifold, okay, and this potential is non-negative. The main example of static manifold is the standard unit per hemisphere, okay, where the static potential is just the height function. A long time problem to classify all the static manifolds is know what are the static manifolds with connected boundary and positive scalar curvature, okay? And in this sense, we have a famous conjecture that question that what are these manifolds, and they affirm that the only n-dimensional compact static triple with positive scalar curvature and connected boundary is given by the standard Howard hemisphere. And the static potential in this case is the height function. Okay. Some developments in this direction, for example, were obtained by Crucial. For example, if you consider this decomposition of the boundary in its connected components, we have, in the case of positive scalar curvature, this inequality, this integral inequality on the boundary, where here is the scalar curvature on the boundary, okay? And the equality occurs if and only if we have a standard Howard hemisphere, okay? And a fortiori, we have just one connected component. This inequality in dimension 3 can be used to prove an important lower bound for the boundary, for the area for the boundary, okay? And this was obtained by Bolken, Gibbons, and Horowitz, and they showed that if you have dimension 3 and the boundary is connected, so we have this bound for the area, and furthermore, the equality holds if and only if we have a hemisphere. In fact, also in dimension 3, we have a gap results. In 2015, Lucas Ambrosio proved that in the case where the boundary is connected and we have this limitation for the boundary, okay, then we also can obtain that the manifold is isometric to a up hemisphere. So we have a gap here. If the boundary is between 4p by 3 and 4p, it has to be 4p, and so we have to have that this manifold is isometric to a upper hemisphere in dimension 3. So natural question here is what happens in higher dimension if it exists some upper bounds for the and lower bounds for the boundary, and what happens in metrics similar to static metric in the sense of metrics that satisfies an equation similar to a static equation. So let's begin to demonstrate our results. First of all, we approach new gap results on n-dimensional static manifolds. And the idea here is that all static manifold has an Einstein-associated manifold in the following sense. If you begin with a static manifold, we can consider a tubular neighborhood of the boundary, okay? And we can define a n+1 manifold by the quotient set, where here we have a circle times this manifold union this ball, okay? And with this equivalence relation, okay? And intuitively, what we do here is rotating a static manifold around its boundary, okay? Intuitively, it's this. And with this, we can obtain a n+1 manifold considering this warped metric. And if the original static manifold has constant scalar curvature equal n plus n minus 1, then the Einstein associated manifold is Einstein in this sense. Its Ricci curvature is n plus h, okay? If we have that all surface graphed in the connected components of the boundary are equal to 1, for example, it's possible to extend smoothly the metric H for all n. And furthermore, we have a topological fact that the signature of n vanishes. Okay, so all static manifold, when we have this condition, we can associate n+1 Einstein manifold with this positive constant. Furthermore, we can, using a Fubini type argument, compare the volume of this Einstein manifold and the volume of the boundary of the initial static manifold, following the steps. The volume by Fubini type argument is equal to this. This is equal to this by the static equation. If you trace the static equation, you can obtain this. Here we use integration by parts formula, okay, because the boundary is exactly a level set of 0, okay, and here use that the surface graphs are all equal to 1, okay. So we can relate the volume of the new Einstein manifold with the volume of the boundary in a static manifold. And in fact, for Einstein manifolds, we have the Bishop-Gromov comparison theorem. So we can bound this volume by a volume of a n+1 dimensional sphere. For this, we can obtain this result. This is a limitation for the volume in on the boundary, okay? And the equality occurs if the Bishop-Gromov theorem occurs, so we have a standard hemisphere. So the result of Boker, Gibbons, and Horowitz in dimension 3 occurs in general, okay, for n dimension. Furthermore, we have also a gap result in the following sense. If you have a compact and static Riemannian manifold with positive scalar curvature n plus n minus 1 and a connected boundary, so there is a epsilon that depends of dimension, such that if the volume is greater than the volume of the n minus 1 dimensional sphere minus this epsilon, then the whole manifold is isometric to a standard hemisphere, okay? And the proof here, we have some observation. This is by the relation, okay, between using the Fubini argument that I called earlier. And we have this relation, this recurrence relation between the volume of spheres. Okay. So to prove this result is sufficient proof that the result occurs in a sense for spheres. This is proof that exists a epsilon such that if the volume of n is greater than this, then n is isometric to a standard n plus 1 sphere. Okay. I mentioned here that when you rotate the hemisphere around your boundary, you obtain a n plus 1 sphere. In the argument here is standard. You use an argument by contradiction. And if the assertion is false, we can produce a sequence of Einstein manifolds that are not isometric to a standard n plus 1 hemisphere. And also we can have this condition of convergence in the volume. So this sequence we can prove that this sequence converge, okay, using some arguments on compacity. And we deal with a contradiction to the fact that canonical metrics in this sphere are isolated isometrics. Okay, this is an idea of the proof. So let's approach some volume comparison to other types of manifolds that are related with static manifolds, and we will introduce now. So we can consider a connect smooth manifold with boundary, okay? Fix a metric in the boundary and consider the set of all metrics in this manifold such that the restricted metric to the boundary is exactly the initial metric gamma. So we can consider the volume functional in the class of metrics, and furthermore fix a constant and consider the subset of all metrics in this set such that the scalar curvature is constant equal to k. Recently, Corvino, Eichmann, and Miao give a variational approach for the subject, and in fact study critical point of this functional, the volume functional. And Miao and Tan, for example, proved that if you consider metrics in this subset, and with the property that the Dirichlet eigenvalue of this operator is positive, they proved that the metrics are critical points of the volume functional if and only if exists a smooth function in the manifold satisfying this equation that is very similar to static equation. And in this case, we say that a metric is V static with potential function lambda, and the manifold is a V static manifold. Okay, this is very similar to a static manifold. Remember that in the static case, this right member is 0. Okay. Some properties of this type of metrics are similar to static metrics. For example, metrics of this type has constant scalar curvature, but its boundaries is not totally geodesic, but totally umbilical. Okay. And you can assume that the scalar curvature is equal this constant. So a rigidity result approached by Miao and Tan was that if you have a compact V-static manifold, which is either Einstein or simple connected and locally conformally flat, then we can prove that if the boundary is connected, the manifold is exactly one of the rigidity models that are the geodesic balls in a simple connected spaced form. And the purpose here is approach some related results of limitation of the boundary in this type of manifolds, okay? And the main tool here is the Porojaev chain identity that we state now. If you have a compact Riemannian manifold with boundary and consider any vector field in this manifold, then there holds this integral inequality, okay? This is for any field and any compact Riemannian manifold. The proof of this identity is very simple. We just use integration by parts formula and Bianchi identity, the second Bianchi identity. And this type of identity was well used in our case because in our case we have constant scalar curvatures, so the side benches. And if you choose x like exactly the gradient of the static or the v-static potential, we have a relation between the Hessian and the Ricci traceless tensor, okay? So we have an important relation here. So the first result for v-static manifolds in a joint work with Barbosa and Lima says that if you have a compact v-static manifold with boundary decomposed of this form and the scalar curvature normalized for this form, then the following integral identity holds, okay? And in particular, we have this inequality, integral inequality for the boundary, with the equality holding if and only if we have that the v-static manifold is exactly the geodesic ball in a simple connected space form, okay? We observe that this integral inequality is a crucial type inequality for the v-static case, and in the on-static case, we extend the crucial inequality for the case where the curvature is negative, okay? So the idea here is just applying the Porojaev chain equation, consider the vector field like this gradient, okay? So using the v-statistic equation, we have this relation, and we can use also that the normal vector field on the boundary is just this vector because in fact the boundary is a level set of lambda, and we deal with this inequality, and the equality occurs if and only if the manifold is Einstein, and we can use the result of Miao and Ta to obtain the rigidity, okay? So some corollaries related with this theorem. First, this, if you have the other inequality, we can obtain that the manifold is always isometric to a geodesic ball in a simple connected space form. And also this result, where you use just the Gauss equation to approach, okay? And we can observe that this is very similar to crucial inequality, just observing that we have this term here, where hi are the mean curvature of the connected components in the boundary. Observing that in the case where you have a static manifold, these don't appear here, okay? And have this inequality, where the equality holds if and only if we have all the manifold is isometric to a geodesic ball. So to obtain this, we just use again the Gauss equation and the previous identity, okay? In dimension 3, we have a special case here because we can use the Gauss-Bonnet formula to obtain a relation between the Euler characteristic and the area of the boundary, okay? In fact, some characterizations. First, we have this, okay? in a general compact V-static manifolds with this condition, we have this limitation of the volume in a V-static manifold. And to demonstrate this, we just again use this integral inequality and trace the V-static equation, okay, to obtain this with integration by parts, and again using the inequality, okay. And in dimension 3 we have this important topological classification. If you have a compact V-static manifold with a connected boundary, okay, and normalize the scalar curvature, if epsilon is equal to 1, and assuming that this new condition in the mean curvature, then sigma is diffeomorphic to a two-sphere, okay. And here you use just the Gauss-Bonnet formula, okay, in dimension 2 to obtain this. And this is positive in the case where the epsilon is non-negative, and in the case where epsilon is equal to minus 1, we use the additional condition to age, okay, to obtain this topological classification. This permits obtain this limitation for the volume from the boundary, okay. This is very similar to what happens in static manifolds. It's like a Boken-Gibbons-Horowitz upper bound for the boundary in the case of V-static manifolds. So we can obtain also using this. And furthermore, the equality of this upper bound holds if and only if we have the models of rigidity. This is the geodesic balls in a simple connected space form. Okay. And in dimension 5, we can also use the Gauss-Bonnet theorem to obtain also a limitation for the area that depends of the topology of the boundary. Okay. Other result that we can approach here, it's a result that first was approached by Miao and Tan, and they consider a V-static manifold in this case, and divide some case of zero curvature and negative curvature, okay. And in fact, the result here is the result for geodesic balls, where we can compare the geometry of the boundary of a V-static manifolds and the geometry of a sphere, okay. In fact, we observe that we can extend this result for any dimension and also for n sign of curvature by this result, okay. So if you have a V-static manifold with connected boundary, okay, and if you assume that our boundary is isometric to a totally umbilical upper surface, and we have this limitation for the mean curvature, okay. Also, the equality holds if and only if we have a geodesic ball in the corresponding cycloconnect space form. We observe that this condition is exactly the same condition in the hitch in the normal direction, okay. It's the same comparison. And to demonstrate this, we use just the Gauss equation for the boundary and for the upper surface that is isometric to the boundary, okay. And so we can sum these two equalities here. We have this. We can integrate this equation, okay? And in fact, here we have a limitation for this integral of this side by the first theorem, okay? So we have also a limitation for this. And the equality implies that we have an Einstein manifold and you use the characterization result from Miao and Tan, okay? The last topic of this lecture is about M-quasi-Einstein manifolds and some volume comparisons for the boundary here. So we motivated this study for this condition. A word product is a product of manifolds with this metric, okay? When you can consider this like the base of the warped product and this like the fiber of the warped product, okay? And a question proposed by Bess's book was search about warped products to give new examples of complete Einstein manifolds, okay? And in this sense, we have in this same book the following proposition that a warped product is Einstein if these three conditions happens, and you observe specifically this condition 2 here, okay? So if you consider Riemannian manifolds that satisfies this second equation and consider Einstein equation, you can produce Einstein manifolds of higher dimension. Inspired by this, we can define a generalized M-quasi-Einstein manifolds like a triple, where this is a complete Riemannian manifold and f is a smooth function satisfying this equation that again is similar to static equation. Remembering that static equation we have m equal to 1, okay? And in the case when you have boundary, we consider that this function vanishes precisely on the boundary, okay? And the case where the boundary is empty has been studied for many authors like Kin and Shui and many others, okay? And after this initial study of manifolds without boundary, Petersen and Willy, by using similar tools, obtain also some properties of M-quasi-Einstein manifolds with non-empty boundary, okay? Some observations here is that when the boundary is not empty, it is totally geodesic, and again, these functions are constants along the connected components of the boundary, okay? If you define the function phi in the interior of sigma by this relation, the equation of M-quasi-Einstein manifolds becomes this, and this is an important extension of some well-known equations. For example, this is the M-Bakr-Emmer heat tensor, and some particular case of this equation are when phi is constant, we have the Einstein manifolds, and when m is equal to infinity, when we have the heat solitons here, okay? So this concept extend many others that are well known in the literature, okay? So we can use again the Pohojayev chain identity to obtain similar results in generalized and M-quasi-Einstein manifolds. For example, we have also this relation in M-quasi-Einstein manifolds, okay? This integral identity also occurs in M-quasi-Einstein manifolds. And in fact, in a joint work with Santos, we we can obtain a crucial type inequality on the boundary in M quasi-Einstein manifolds. Okay, if you have this additional condition here. Okay, so we can obtain also these results. And furthermore, also the equality occurs if and only if the whole generalized and quasi-Einstein manifolds is isometric to a hemisphere. Okay, and for example, this is an important rigidity result, because if you have a compactly generalized and quasi-Einstein manifold with normalized curvature constant equal to n plus n minus 1, if you consider that the boundary is isometric to n minus 1 dimensional sphere, then the whole manifold is a hemisphere of Sn. Okay. Other corollary is that in dimension 3 we can use again the Gauss-Bonnet theorem to prove that in a compactly generalized and quasi-Einstein manifold with connected components such that this occurs and the scalar curvature is positive, we can prove that the boundary is diffeomorphic to a tree-sphere. Okay. Finally, we have this result that is a volume comparison for the boundary in a generalized and quasi-Einstein manifold. Okay, it's like a theorem of the sense of Boken-Gibbon-Horowitz upper bound also. Okay, but in this case, in this special case of generalized and quasi-Einstein manifolds. Okay, and this happens for n dimension here. Okay, we observe this. We can just approach the proof of this result, and we have some conditions, additional condition here, this and this. Okay, and alpha is this constant. To prove this, we first of all, from this condition, we get that exists a delta such that we can take the infimum of this set and consider that this is n minus 2 times delta. Then we have this condition here. Okay. In particular, from the Bonnet-Myers theorem, we have that the diameter of the boundary is less or equal this quantity. And for this limitation, we can use, again, the Bishop-Gromov theorem to prove this inequality, this volume comparison between the area of the boundary and the volume of n minus 1 dimensional sphere. Okay, so we can consider a vector field such that this is true. Thus we have this, okay, using the previous inequality, and using this condition we get from the crucial type inequality that this happens. So we have this, okay, where it is the scalar curvature of the boundary. Finally, join these two facts, we get this condition, okay, and we get the desired inequality. And furthermore, the equality occurs if and only if we have that our M quasi-Einstein manifold is also Einstein, and using this condition you can prove that we have a round hemisphere. Okay. Also in dimension 5 we can prove a similar result using the Gauss-Bonnet theorem. So this is all. Thank you again, and all questions we can email me.